In this video, we will be discussing bias and variability of statistics. Definition: sampling distribution. A sampling distribution is a distribution of all samples of some particular size. Alright, this next part is not necessarily for your notes. This is a review, but if it's not a review for you, if it's new, you should copy it down. One of the big ideas that we have in this class is the difference between a population and a sample. All right, a population is some large group that we want to know something about. Maybe it's the entire United States. Maybe it's all females. Maybe it is the whole world of cats. All right. Well, very often this entire population, it's hard or even impossible to learn everything about them. Even one particular thing, if we wanted to know the size, the height of all adult American men, it would be virtually impossible to go out there and measure all of them. So what we do is we take a little subset of that. We take a part of this sample, all right? We take a part of this population. And this subset of the population, this subset is called the sample. It's a part of the population. Subset of the population. Okay. Well, we'll have numbers from each one of these. From the population, we have parameters. A parameter is some number describing the population. From the sample, we have this course, statistics. A number describing a sample is a statistic. Well, let's look at it, a couple of examples of these. Parameters and statistics. One particular thing that we described often is the mean, okay? The parameter version of the mean, we use the Greek letter mu. It's looks like a little U with little curly sides, all right? The statistic companion for that is x bar. X with a little bar over it, or y, or whatever arbitrary variable that you want to use here. Another particular quantity we describe is proportion. This is a percent. The parameter is p. The statistic is p hat. We've talked about the standard deviation. The parameter standard deviation is the Greek letter sigma. Well, our statistic is the letter S. And I'm going to introduce a new one today, size. All right. The size of the population, the parameter, we use capital N. Our sample size, we use lowercase n. All right. So these parameters, we are rarely going to know for certain, but these statistics we can find, and we are going to, one of the culmination of this class is using some number, some statistic, like x bar, and taking a stab at what the parameter is, mu. And this idea of taking x bar and taking a stab of mu, this is inference. That is, it's drawing a conclusion with some confidence. We can know something for certain about our sample, but our population, typically we won't know for certain, but we can get some idea by looking at our sample. Okay. So a sampling distribution is a distribution of all samples of some particular size, and we will investigate that further later on. Right now, the definition is sufficient for us. Bias. We've already been introduced to the concept of bias. Earlier, for our project number 1, we had survey bias. We noticed that the way we asked a question systematically favored some response. We could ask a question in a certain manner that would get a response that we were more interested in. And so this concept of bias with our sampling distributions is very similar. We say that a statistic is biased. A statistic is biased if its sampling distribution is not centered at the population parameter. All that's saying is it's not centered where it's supposed to be. So back to our project number 1, you asked a question in such a manner that you didn't find really what you were trying to find. You biased the results. You centered your sample was not a good estimate of whatever particular parameter you were trying to learn about. Variability. The variability of a sampling distribution is its spread. And again, we see these two key concepts we've talked about often in this course. Center and spread. Bias deals with center, variability deals with spread. All right, let's look at some specific examples of what I'm trying to communicate here with bias and variability. Example. Well, let's say that we're trying to find the height of adult American women. Okay. Well, that height exists, and it has some mean. And I'm not sure what that mean is, but I'm just going to mark it here with mu. I believe it's somewhere like 5'5", 5'4.5", but let's say that we don't know what it is. Well, what we could do is, here's our whole population of adult American women. This is American women. Well, I could pull a sample out of here, and this sample might be of size 6. This meaning there's 6 women that I measured, and when I measure these 6 women, they end up having some mean. All right. And it doesn't matter what it is here. If we were to do this over and over again, if we pick many, I call this x bar 1 and this next one is x bar 2. All right, and it's also N6. Okay, this is my second one, and I could find another one. I could keep doing this over and over again. All right, if I were to graph these and they were all centered real nicely, here's my x bar 1 and here's my x bar 2 and over here's my x bar 3 and I've got another one and another one and another one, and maybe they end up being kind of piled up in this fashion. They're all kind of piled up nicely real close to this mean. When we have a situation like this where our sampling distribution is real tight together and it's centered where we want to see, it's not biased. Our distribution, this is a distribution of samples, it's centered right where we want it to be on the population mean, and it's not spread very much. This situation here is low bias and low variability. All right. What I'm saying is the low bias means it's centered roughly where it's supposed to be. We're trying to hit this population mean. I don't know what it is, but we're trying to hit it. And we took all these samples and they were kind of close to this same value. Low variability means they're not spread out very much. Okay, that's low bias and low variability. Well, let's say that we do this again. We're looking for this value mu, all right, and we do some more sampling, but this time we don't sample so well. Maybe we sample the women's basketball team at our local college, and so this time all of our samples are not centered on the mean. Okay, here's where we want to be centered. This is the true value, but here all of our samples, they just happen to be greater than that for whatever reason. Well, this situation is high bias, not high because it's above, but high because it was improperly centered. Remember, bias deals with center. And here's our sampling distribution. It's centered here. It's not centered where we want to be. It's high bias, but it is low variability. That is, it's not spread out very much. Like this one, there's not much spread, so it's not spread much, but it's not centered where it's supposed to be. Okay. Now let's look at this again. So we have our population parameter, and this time we take samples, and our first sample is over here, and our second sample is here, and our third sample is here, and our fourth sample is right there in the middle, and our fifth sample is here. Maybe we had another one over here and one here. Okay, and here you can see they're spread all over the place, but they're centered about where they need to be. Maybe there's another one here and another one over here. So this situation is spread a great deal, but it's centered properly. Since it's centered properly, we'll say there's low bias. Like this one, our sampling distribution, our distribution of samples are centered over our true mean, but it's very spread out. It's going to be low bias and high variability. This one is low bias. That is, it's centered properly. Bias deals with center, but it's high variability. It's spread out. Our statistic is quite variable. It changes a great deal. We had one that was very high and one that was very low. Okay. All right, last situation. I'm sure you can figure out where we're headed here, but here we're looking for high bias and high variability. So if we have our population mean that we're trying to find, and this time our distribution is really spread out. It's really spread out. And it's not centered where we need it to be. This is the worst of both worlds. This situation is high bias and high variability. That is, we weren't centered where we wanted to be, and they were quite spread out. This is the worst of both worlds. As statisticians, this is what we're looking for. We want our situation to be tightly clumped and centered where we're supposed to be, because essentially each one of these X bars here could be where we're going to base our inference on. Thus, we want any of these to be close to the true mean. If we're real far spread out, that's going to be fine if we have one of these in the middle, but we have one of these on the end, then our inference may not be too good if we're only taking one sample. In this case, we're going to miss our mean no matter which one of these come, and here we have the worst of both worlds. All right, this situation of bias and variability is analogous to a concept you've studied previously in science, most likely. Now I'm Googling accuracy and precision. And this is probably a diagram that you've seen previously in science. If we were conducting an experiment or we were doing some measuring, we hope to have a situation like this where we're hitting the bullseye regularly. It's accurate, that is, we are centered well, and it's precise. All the shots are close to each other. So this concept of accuracy is like bias. It deals with the center. This concept of precision is like variability. It's how repeatable it's how well clumped our situation is together. Here is one that is accurate but imprecise. This would be like low bias, we're centered well, but high variability, they're spread out. All right. Here is inaccurate but precise. That is, they're all clumped together. They're not spread very much. This is low variability, but it's biased. It's not centered where it needs to be. This would be, in terms of measurement, this is a machine that needs to be recalibrated. Maybe we have a scale that is weighing stuff too heavy all the time. So you would think that this would be an easier situation to fix. And this last one is imprecise and inaccurate. That is, we're not centered where we're supposed to be and they're spread out. This would be the same as high bias and high variability. That concludes this video.